Welcome to this the second webinar. The first one was a couple of weeks ago by Paola, a very nice presentation. So we first thought we'd give a short introduction on why we think a webinar series might be of interest to us. And the most important reasons, I think, is that we really want to see if we can get the most out of the task team number 3. So we all know why that the US AMOC science team has been put into place to try to promote AMOC science and to facilitate collaborations. But we may have the feeling that these annual or biannual meetings may not be very suboptimal to actually establish these connections and to exchange ideas for collaborative efforts. And that's the reason why we think that a webinar series where we kind of informally discuss some hot topics related to the AMOC might be helpful. So we try to have these webinars to discuss pressing AMOC-related issues related to the variability and stability of the AMOC, and hopefully exchange ideas that might lead to some collaborative efforts or so, maybe some proposals. Next one, please. We need volunteers, otherwise this is going to be the last webinar of the series. So please don't hesitate to contact us if you want to present this webinar in the next couple of months or so. Steve, do you want to add to this? Or?
I just add that originally we came up with this salinity advection feedback focus group as a result of our November telecon, and this is intended to address 2 of our Task Team 3 priorities. We have a near-term priority that's written in the last annual report to investigate the role of freshwater forcing in South Atlantic freshwater transports in determining the variability and stability of AMOC. But we also have a long-term priority to try to synthesize results from theoretical, idealized model, and complex GCM investigations into common conceptual frameworks. And so the idea of this particular salinity focus group was to try to address both of those near-term priorities and be proactive about making progress on those fronts.
All right, very nice. So let's get started. So the topic of today is the salt advection feedback in eddying ocean models. Next one, please. So just to make a quick summary in the beginning, I think that theory and low-resolution models suggest that the salt advection feedback is critical for the stability of the Atlantic meridional overturning circulation, but it is not quite clear whether this advection feedback in itself, but also the implications in terms of the AMOC stability really carry over to an eddying ocean. Next one, please. So I think some of 1961 was the first to actually recognize the importance of the salt advection feedback. Next one. He considered this system of two basins, basically one a cold and fresh basin that he indicated as a subpolar basin, and another basin that is warm and salty, which would represent a subtropical basin. They're connected at the bottom by like a capillary, but they are also connected at the top by this overflow. Next one. The flow rate in his model is proportional to the north-south density difference, and in that respect is both responding to the north-south temperature difference, delta T, and as well as the north-south salinity difference. So if you have this positive circulation, which would be anti-clockwise in this picture, it would mean that the temperature actually drives the flow, whereas the salinity provides a break. So another aspect of this salt advection feedback is that the meridional density difference depends on the advection between these boxes. And in that case, the stronger flow would advect more warm water from the subtropical box to the subpolar box, and would hence tend to reduce the north-south temperature difference, and hence tends to reduce the flow rate. And this is a negative feedback in the system. On the other end, a stronger flow also reduces the north-south salinity difference, as it would affect relatively salty water from the subtropics north into the subpolar basin. And this tends to enhance the flow rate. It reduces the breaking effect of salinity, and hence it provides a positive feedback on the system. Next one, please. So this concept was expanded on by Stefan Rahmstorf in his 1996 paper, who basically added a Southern Ocean box to Stommel's equatorial or subtropical subpolar box. So now we have a subpolar box for the southern hemisphere, or basically representing the rest of the world ocean. We have two tropical boxes in the Atlantic, and we have the North Atlantic subtropical box. Next one. The most critical parameter in this system is F1, which is the fresh water that's imported into Atlantic either by the excessive precipitation over evaporation or by the wind-driven gyre exchange in the South Atlantic. So in a steady state, next one. Okay. So that the little black arrow that is on top of the T1 was supposed to be a big arrow that's green, and which indicates that these atmospheric freshwater fluxes in steady state has to be balanced by freshwater export by the AMOC, basically. So given this system, Rahmstorf did the math and he came up with this flow rate equation that's now shown on top, which is mainly dependent on the temperature difference between the northern subpolar box and the southern ocean box, but also depends on this atmospheric flow rate F1. It does not depend on the intra-basin freshwater flux F2, which is a deviation from Stommel's box model. Next one. Based on this flow rate equation, he came up with this schematic equilibrium diagram. On the left, you have the situation where the Atlantic is evaporative, so where there is a net freshwater flux out of the Atlantic through the atmosphere or by the wind-driven gyre, and hence an input of freshwater by the AMOC. And this would lead to a stable one stable solution that is driven both by the temperature and the salinity. On the right side, on the other hand, we are in the precipitative regime, where the Atlantic receives an excess of fresh water through the atmosphere. In this case, next one, we would have both the thermally driven equilibrium that is braked by salinity, as well as a reverse circulation, which is shown at the bottom, which is a salinity-driven equilibrium. That is reversed, so that it does not have any North Atlantic deep water formation in the subpolar North Atlantic. Next one. This concept of this multiple equilibria was made explicit by Henk Dijkstra and his group, and I was part of that. And so we calculated equilibrium diagrams for fully three-dimensional global ocean circulation states. And this is one example from Henk's 2007 paper, showing on the left side the monostable regime, and on the right side the bistable regime. And as you can see, these are delimited by the limit points or settlement node bifurcations L plus and L minus. Next one. Henk's contribution, which is very important, I think, is that the location of this limit point L minus coincides exactly with a qualitative change in the fresh water budget of the AMOC. So in the monostable regime on the left, the AMOC imports fresh water, whereas in the bistable regime on the right, the AMOC actually exports fresh water. So this metric and this freshwater balance is given by this metric MOV that appears much more in the literature since then, and which is basically defined here at the bottom by the salt transport that is induced by the zonally integrated flow across about 34 degrees south or so in the South Atlantic, the exchange between the Atlantic and the rest of the world ocean, if you will. Next one, please. So to summarize, in these models, if the Atlantic overturning circulation exports fresh water, then it suggests that we would be in a bistable regime, and in that case the salt advection feedback is positive, whereas if the AMOC imports fresh water, then we are in the monostable regime and the salt advection feedback is negative. The important thing to note here is that observations, or a few limited observations that have looked at this issue, suggest that the AMOC actually exports fresh water, suggesting it would be in a bistable regime, whereas the majority of climate models suggest that the AMOC imports fresh water. So here's the question, whether these climate models really overestimate the stability of the AMOC in our current generation of climate models. Next one, please. So, but of course we have these concepts, and this intuition has been based on relatively low resolution ocean models, going from 1 degree coupled GCMs, which is the highest class, all the way down to these box models from Stommel and Rahmstorf. But it's not really clear whether these concepts carry over to an eddying ocean. Next one. In a recent study by Matthijs den Toom and Henk Dijkstra, in which I was involved in as well, we looked at this problem from a global eddy-resolving ocean model perspective. So we configured this global ocean model, parallel ocean program, or POP, at a 10th of a degree resolution, and we ran it for 50 model years. And we compared the control experiment of this simulation with a perturbation experiment in which we put fresh water around Greenland to force the North Atlantic in that way. And we also compared two identical simulations, but in non-eddying ocean configurations at a 1 degree spatial resolution. Next one. So the first thing that we looked at was to see if there's indeed, if we could find a relationship between the strength of the overturning circulation and a characteristic north-south density difference. And on the vertical axis, we see here for the non-eddying case the strength of the AMOC. On the horizontal axis, a characteristic meridional density difference. And the black symbols that you can see there are for the control run, and we see that there is hardly any change in time in the strength of the AMOC or this north-south density difference. But the red line, the red symbols indicate the transient perturbation experiment, and there we see very clearly that the overturning strength decreases when you go towards the lower left corner, and we also see that the north-south density difference decreases. So this is consistent with this diabatic view that's presented in these, for instance, the Stommel box model, and probably in the low-resolution ocean models. Next one. However, the situation for the eddy-resolving model is much more ambiguous. Again, we see the black symbols that are kind of clustered in the top, which show that the AMOC doesn't really change that much, and neither does the north-south density gradient that we diagnosed. But we see that for the transient integration, we see that the overturning strength decreases, but this is accompanied by an increase in this north-south density gradient. So this is something that seems to be inconsistent with this view, basically, of the north-south density difference driving the overturning circulation. Next one. So next we looked at the fresh water flux across 34 degrees south in the Atlantic. And now we see again for the non-eddying case that the black line is the reference case. It has a positive fresh water flux. So this means that the AMOC imports fresh water, much like most of the coupled climate system models that are around. So we also see that the red line is the perturbation experiment, that we see a reduction in time with this fresh water flux, which in this case is a result of a reduction in the overturning strength. So we have this reduction in the overturning strength reduces the freshwater import, and this is actually this negative salt advection feedback in action, and this is fully compliant with this picture painted by the Stommel and Rahmstorf box models. Next one, please. However, the situation for the eddy-resolving model is again very much ambiguous. So we even see that for the reference case, we see that initially this overturning freshwater flux is positive, but then it starts to decline pretty significantly to zero and values below zero after the 50 years of integration. We saw in the previous plot that the AMOC doesn't really change that much on this time scale. So in this case, what we're seeing here is that the freshwater flux across 34 degrees south changes due to a drift in the salinity at 34 degrees south, rather than being in response to a change in the AMOC strength. For the perturbation experiment, we also see a similar decline in this freshwater flux. Initially very much in line with the reference case, and you can argue that in the end it starts to decrease a bit faster than the reference case. So we looked at this difference in a bit more detail, hoping that expecting it to be related to a slowdown of the AMOC, but we could not find evidence for that, and instead we conclude that this increased reduction of this freshwater flux, that this increased reduction in the freshwater flux was also due to changes in the salinity at 34 South rather than changes in the AMOC there. So this picture does neither support this salt advection feedback paradigm presented by the Rahmstorff and Stommel box models. All right, so then next one, please. Paula, Cessi, and Christoph Wolfe have done a lot of work on these quasi-adiabatic models. So this is a different paradigm from what is usually being modeled in low-resolution ocean models and also these simplified box models. So rather than being responsive to a north-south density difference, these adiabatic pole-to-pole circulation systems are driven by the wind-driven upwelling in the Southern Ocean. And they are enabled actually by the joint buoyancy outcrops in the Northern Hemisphere and the Southern Hemisphere. And in these models of Wolfe and Cessi, it is assumed that actually the Northern Hemisphere is lighter than the Southern Hemisphere. So this overturning circulation actually goes against the prevailing density difference between North and South. In a 2014 paper, they looked at the salt advection feedback, and it did show that this advection feedback is active, is positive, because it reduces the north-south buoyancy difference. So the buoyancy is higher, in the north, but the salt advection makes it more dense, allowing more larger overlap between the isopycnals in the south and the north, enabling a stronger overturning circulation. Next one, please. In a 2015 paper, they followed up on this concept and looking at the possibility of multiple equilibria. And they actually found multiple equilibria even in this quasi-adiabatic context. So they found that the direct circulation is adiabatic, and is shown here by the overturning stream function in the left center plot here, the orange and red plot. Strong overturning cell with most of the upwelling in the Southern Ocean, where there are no continents to block the zonal transport there. But they also found a reverse circulation, which they concluded is diabatic instead. So that is the lower plot showing a reversed overturning circulation cell. And here most of the downwelling takes place just north of the latitude of the Drake Passage. And on the right side, you see the results of hysteresis experiments that they did, showing this multiple equilibria regime. Next one, please. So these are kind of the different paradigms, I would say. So there's this diabatic paradigm where the AMOC is proportional to a positive north-south density difference. So it's assumed that the northern hemisphere is heavier than the southern hemisphere, and that this density difference drives the overturning circulation. The salt advection feedback is positive if the AMOC exports fresh water from the Atlantic, and it's negative if the overturning imports fresh water into the Atlantic. And in this concept, the MOV, so the design of the fresh water flux into the Atlantic, indicates whether the AMOC is in a bistable or a monostable regime. The adiabatic paradigm is quite different, and the AMOC is, in this case, strongest if the north-south density difference is smallest, actually. And that's assuming that this density difference is negative, and that the northern hemisphere, the northern subpolar region, is lighter than the southern subpolar region. It is clear that the salt advection feedback is positive in this case, but it is not clear at all what determines the bistability regime. So is there anything of this diabatic paradigm that carries over to this adiabatic paradigm that'll tell us something about the bistability? Next one. And this is my last slide. So how can we reconcile these two paradigms? Our intuition is mostly based on the diabatic view that I presented. But now with this adiabatic paradigm, how do they play together, basically? Are they totally different, or are there some concepts that carry over from the one paradigm to the other one? So is this, another question, is this MOV metric still relevant as a stability indicator, or is it just only relevant in our diabetic world, and can we think about ways to tackle this problem in a systematic way, possibly using a hierarchy of models. So this is basically my presentation, and I'd like to invite comments from here.
Thanks, Wilbert. Yeah, with that we could open discussion, and just a reminder, all of you are on mute. It may be easiest if you raise your hand and I can call on you to keep the questions going a little bit, and we'll go that way. So Paula, go ahead.
Yes, I just have a clarification question on some of your earlier slides where you doing the eddy-resolving model, and I guess I didn't understand what you were varying. What was the delta sigma 0 that you were varying? Sorry, can you go back?
Yes.
The previous one.
Yes, one more.
No, one more. Yeah, what was varied at the?
So this was just a diagnostic. So we did this hosting experiment, putting fresh water in the North Atlantic, and we diagnosed both the AMOC as well as a characteristic north-south density difference, basically. So these were both diagnosed from the same run.
So doesn't this suggest that the eddy-resolving, I mean, one possible interpretation is that the eddy-resolving model is in the adiabatic regime?
Yes, that is definitely possible, yes.
And then the other question that I had, if you go 2 slides forward. Yes, that one. So this MOV is drifting, but are other quantities? So my question is this MOV drifting because you're not in a statistical steady state? Because 50 years is not very long. And so my question is whether you looked at other diagnostics that instead suggested that other quantities were in steady state, and so this is not just a transient due to the initial transient.
Well, I think the main conclusion is that at least for that even for the control case, that we're still in a non-steady situation. Basically, there's still considerable climate drift.
So we don't know.
Yes, correct.
Okay.
So that's probably one of the problems that we have to deal with if we want to go to fully eddy-resolving. I mean, even in your publications, you ran all these simulations out for 5,000 years or so and looked at steady states. But is there something that we can infer even from transient simulations? Because definitely in these global eddy-resolving models, we're mostly confined to just looking at short-term effects, basically.
Great, thanks, Paula. Other questions from folks? Dong Zhao, I'm going to try to take you off mute, and hopefully, go ahead.
Hello. Go ahead. Yeah, this question is about how long does the model need to reach the equilibrium state. So Paula, your model resolution is really high, and you run that for thousands of years. So what could be the shortest time scale that you think the model can achieve the equilibrium state?
Sorry, who are you asking?
Dong Xiao, I ask you, your model, you run your model, which is high resolution for thousands of years.
No, my model was low resolution, not high resolution.
It's low resolution. Okay, then we don't know. So my question basically was to ask, what could be the time scale for the models, eddy-resolving models, to achieve the equilibrium state? I thought your model has been running for thousands of years in high resolution, so you might have a better idea.
Yes, well, this is obviously a big problem in the world of high resolution ocean and climate modeling, that we'll never be able in our wildest dreams to reach a statistical steady state. So we have to think about ways to get around that. Maybe we don't even want to reach a steady state because we may not like what we see.
Well, I guess one of the questions has always been is there a way to accelerate convergence and we know how to do that for low resolution. Francois Primo has these methods to do that, and I don't think they can be used for eddy-resolving directly, but one could try and start with maybe low resolution and with the same parameters and parameterized eddies as an initial state, and then turn the eddy outs on. But I don't know. I mean, you still have problems.
Well, even Francois' approach does not address the spin-up of the full ocean circulation. It only addresses facilitates the spin-up of tracer distributions given a certain ocean state.
Yes,
so
but that's the slowest part. The tracer one is the slowest part.
That is right, but there's no iterative procedure where you can actually apply that to the temperature salinity field, then adjust the flow field, and then readjust the salinity and temperature field to spin up both the flow as well as the temperature and salinity fields in an iterative procedure, right?
Right. Well, just to be clear, Francois' method, that method does not apply to active tracers. It's only for passive.
No, I agree, but the flow is going to be balanced very quickly. So you could actually just assume that it's in geostrophic balance and then do something about the equator, and then iterate. It's not that hard because we know that the geostrophic balance is very, very, very good approximation. And then that just becomes a diagnostic. Sorry.
No, go ahead.
Done.
You're done. Okay. We have a couple more folks with hands up if we want to move on. Zoli, you had a question?
Yes. I guess I'm just wondering, you talked about eddying versus non-eddying models, but I wonder if you could somehow tweak the eddy diffusivity parameter in either case as a way to look at the sensitivity to mixing, because we know that mixing does impact the strength of the overturning, and so it might have an impact on the stability of the overturning.
Right, and that's basically the approach that Paula is taking in her model, to try to get the background diffusivity as low as possible, basically, and just enough to keep the model stable in a sense.
Yeah.
But that approach is usually not taken in coupled climate models, and maybe that is a way that we could proceed in this respect.
This is Gökhan actually. I have done quite a few 600-year fully coupled integrations. I presented some of that thing in the AMOC meetings, and those integrations actually change various mixing coefficients in the ocean model. If anybody, we can take a look at that actually, if AMOC stability is changing.
That'd be very interesting. Maybe you could present sometime.
Yeah.
Another volunteer. Steve, did you have a question?
Yeah, I had a question for Paula. I thought that some of those early Wolfe and Cessi papers you did use an eddy-resolving version of your idealized model.
Yes, but only with one tracer. There was no salt.
So I guess I was thinking, wouldn't that be the natural framework for testing the sensitivity to resolution is in an idealized framework like that?
Yes, I think so. But again, we had a small domain and smaller than usual, right? Which I'm glad we did.
Right. Well, that's the advantage over a GCM.
Right. So no, you're absolutely right. That would be still a lot of work, a lot of computations, because we in order to be in statistical steady states, we actually integrated for hundreds of years. So like 500, 600, and then when we perturbed something in, it was on a state that was already close. So, But yes, I agree. That would certainly be the case. It would be a good thing to do.
Great. Do we have any other questions from folks? Marlos, go ahead. Marlos, maybe you should check and make sure your audio is off mute. If you're using, looks like you're using a headset.
Oh, hello. Can you hear me now?
Hello. Yeah, you're a little quiet.
Oh. Yeah.
Better. Go ahead.
Yeah. So, my question would be about the azimuthal component or the gyre components. In two models, I've seen that the MOV and the azimuthal component, they cancel, they balance each other. And I don't know if somebody has investigated the role of the gyre component on the salinity, the import or export of salinity to the Atlantic.
Yeah, we're working on it, but I would say, generally speaking, I would say the gyres act a bit like diffusing and trapping water. So they diffuse within they trap within a certain region of the gyre, and then they expel the gradients at the outer rim of the gyres. So.
Right.
So they certainly have a very important role. I mean, no doubt about it.
So another set of experiments by Zheng Liu and some groups in the Netherlands, I believe, where they actually played with this the gyre-induced freshwater import to change the stability of the AMOC, to bring it in from one regime in another, to basically use it as an external forcing factor on the AMOC. So those are relevant studies as well, I believe.
So who are the authors? Say again.
Zheng Liu, LIU, the University of Wisconsin.
Oh yeah.
Madison, Wisconsin.
All right. Okay. Yeah, thank you.
Sorry, in what year were these published? These papers by you, more or less?
Probably 2005 range or so, maybe 2007, 8, something like that.
Okay. Well, it looks like we're petering down.
Yeah.
Yes. Right.
So,
all right.
Can everybody hear me?
Yes.
Yes.